Hello, class. This will be the last lecture, recorded lecture for probability finish in section 5.3, which I think is the most complicated section we've done so far. And so just a couple other loose ends to clean up. The first one is explaining the difference between probabilities given this idea of sampling with replacement or sampling without replacement. And if there is replacement when you do the experiment, then we call that independent event. And when it's without replacement, it's a not independent event. And the classic example is for those of you that like to play cards, and especially if you're calculating probabilities of poker, etc. Those calculations are dependent because it depends on who has the other cards, right? How many clubs, how many aces, etc., etc. And so let me just show you, hopefully, a reasonably simple example, not using decks of cards. But let's say we have a bag of marbles. And in this bag, we have 3 blue marbles, 2 green marbles, and 1 yellow marble. And in this bag, what is the probability of pulling out a blue marble in a second given the first marble was blue. Well, what do we do with this? Well, what did we do with the first marble? We pull it out and it's blue, right? And so did we put it back into the bag or did we keep it out? And I am really bad here at spelling. And so that's what we mean by replacement or not replacement. So let's say we replace the marble, first marble. So this is replacement. So what ends up happening? We take and we pull out the blue marble. And then what do we do with it? Well, we take the marble and put it right back in. And then we pull out the second blue. And so what's the probability of pulling out the second blue marble, given that we pulled the blue one out and then put it back? Well, you can see it's going to be 3 on the top and 6 on the bottom. So what if it's without replacement? So when you do that calculation, what you do is you pull the first blue one out. So what are we left with? Well, we got rid of 1 blue. So there's only 2 blue left on the top. And there's only 5 left. So you can see we've changed the sample size as well, or the sample space. And we've also pulled out 1 blue. So we've changed the success, the number of blue marbles in the bag, right? So in this case, what we were talking about with replacement, this is an independent event because it doesn't matter what happens to the first one. Since you put it back in there, it could have been a green marble or a yellow marble, doesn't matter. But this is not independent because what happened in the first pull of the marble, or taking the marble out of the bag, affects what happens for the second probability calculation, because not only are you changing the sample space, but you're changing the number of blue marbles that we have in the bag as well. I hope that makes sense. I know that this drawing's a little bit messy, so sorry about that. It's hard to draw on the whiteboard here on the computer. So the last thing we're going to talk about now is the probability that an event occurs at least once. And so this idea of using the complement we're going to be using during this calculation. So let's do a couple examples. And this is actually used when you're calculating the probability of an unlikely weather event occurring. You ever hear of the 100-year floods or the 100-year rains? They have small probabilities. So for those of you going into meteorology, you'll be using a lot of probabilities in these calculations as well. But here we're going to talk about a couple examples. First one is this one here about finding flaws using inspectors. So what it says that if a flaw is present, each inspector has 0.8 or 80% probability of finding it. So let's say the probability of a flaw of being detected is 0.8. And then it says the, whoops, I don't think I'm sharing my screen, but that's okay. I could redo this. So here I'm sharing it. So the inspector's works are independent, meaning that the effect of one inspector doesn't affect what happens to the other, which is nice. And it should be that way, right? Unless they're working together, which inspectors should not do that. And if an item has a flaw, what is the probability that at least one inspector detects it? Okay, so back to the whiteboard here. So the probability of finding a flaw would be 0.8. And what would be the probability of not finding a flaw? Remember, that was the complement, and that was 1 over the probability of finding the flaw. And so that would be 1 minus 0.8, and that would be 0.2. So here's where it gets a little tricky, because what we're trying to do is calculate the probability that the inspectors fail to detect, right? And that is the same as 1 minus the inspectors sorry about that. Let's start this one over. I wrote the wrong thing down here because I just did that up top. That's not the hard part. The idea is, apologize for that, is that the probability that at least one inspector detects the flaw. And that's like, so how do we set that up mathematically? Well, at least one, and this shows up quite a bit in some, especially in, like I said, the weather probability calculations for the 100-year floods and 100-year rains, etc. This is the same as 1 minus the probability of none of the inspectors detecting a flaw. So if you think about that, that's the probability of the first and the second and the third inspector all failing, all right? And so how do we do that calculation? Well, the only way to make this a reasonable calculation is these are independent events. And you remember we put up the problem and it said all three of these inspectors are working independently. So here's the probability of 20% or 0.2 that each one of those inspectors fail. So this would be 1 minus the probability of the first one failing, right? Times probability of this, whoops. Probability of the second one failing, and then times the probability of the third one failing. And so that would be 1 minus 0.2 times 0.2 times 0.2. And so you see that this ends up being a pretty small number. It'd be 1 minus 0.2 to the third power. And so if you did that calculation, you get 0.992. And this is this concept of redundancy. As engineers working in telecommunication industry, we ended up having redundant products in our system. We called it like an N+1 redundancy, where if one of them failed, we still could power up all the loads. And you can see that this number is really quite big, is that the probability of all three of these inspectors not calculating it is really small, or at least one of them finding a flaw is really large. That's 99.2%. So again, in some of the reliability world and some of the weather worlds, we use these types of calculations. So let me show you one more. This one is this idea of using a coin now. So this one is more of what I would consider theoretical probabilities. And here a fair coin is tossed 5 times. What is the probability of it comes up at heads at least once? So when you do this calculation, again, this at least once is the idea of having a 1 minus no heads. And so remember, a fair coin, probability of head would be 1/2. Probability of tail would be 1/2. And if you flip 5 times, what happened the first time does not affect what happens the second time, third time, fourth time, fifth time. So what's nice is this is all independent events. And again, when you do this calculation, there will always be independent events. The calculation for dependent events, very complicated. We're not going to talk about it in this class. And so if you go and think about how this is set up, is the probability comes up heads at least once is the same as the probability that 1 minus the probability that does not come up heads at all, which would be 0 heads. So if you look at the book, they use a lot of these words. Another way to think about it is the probability of it all being tails, right? 0 heads mean probability of them all being tails. And again, they're independent events. So the probability of a head would be 1/2 or 0.5 using, or the probability of tail, exactly the same thing, 1/2. And again, that would be 0.5. So the probability of all of them being tails would be the probability of first one being a tail, so tail 1, times the probability of tail 2, times the probability of tail 3, times the probability of tail 4, times the probability of tail 5. So you could see that this would be 1 minus 0.5, and you multiply it 5 times. So it would be to the 5th power. So it's handy to have a calculator in these calculations. So if you do this, it would be 0.5 to the fifth power is 1 minus 0.03125. So you can see it's a pretty small number if you want to get 5 heads in a row. And so if you did that, the calculation would be 0.96875. So very close to 97% for that calculation. So this is the last part of this very challenging section. This idea of at least once or at least one is the same as 1 minus 0, or it never occurs, does not come up at all. Like we said, the inspectors, none of them found the flaw. In this case, 0 heads, or all of them are tails. And you can see the numbers are going to be really close to 1. So in summary here, this is the objectives that we talked about. The general form of multiplication, idea of conditional probability, which is quite challenging, independent, dependent events, and then the idea of samples with and without replacement. And the last is the calculation of probabilities of at least 1. So that ends the recorded lectures for chapter 3. And again, by far the most challenging is section 5.